So this video explains section 6.4 and section 6.5 because they're very closely related. Okay, we're just going to go through an example that was in the book and look at the solution. So section 6.4 is about creating the model for optimization problems. And an optimization problem means that we want to get an optimal result. So that's the reason we have these systems. We want to maximize profit. We want to minimize cost. That's why this is used in math. So that's what an optimization problem is. And there is a definition. There's a bunch of definitions on page 326 that you could look at. And these are questions that are going to be on your pretest as well. Okay, definitions will be on your pretest. So 3 teams are traveling to a basketball tournament in cars and minivans. Each team has no more than 2 coaches and 14 athletes. No more is a clue word for inequality. Each car can take 4 team members, and each minivan can take 6 team members. No more than 4 minivans and 12 cars are available. The school wants to know the combination of cars and minivans that will require the minimum and the maximum number of vehicles. Create a model to represent this situation. So this is what Juanita did. She said, let M represent the number of minivans and let C represent the number of cars. So first thing she did is she set up variables. Now, interesting here, it says these variables are whole numbers. The reason these are whole numbers is you can't have half a car, okay? You can't. Smart car is little, but it's not half a car, okay? And now there are some restrictions. I said M is a whole number and C is a whole number. A whole number means counting numbers in 0. 0, 1, 2, 3, 4, 5, 6. Those are whole numbers. Okay? They didn't say integers because guess what? You can't have -2 cars. Some more constraints. The number of cars available, cars, is less than or equal to 12. Minivans is less than or equal to 4. So that's what they said. That was right here. No more than 4 minivans and 12 cars. That was some more restraints. And they said the number of team members is 4C plus 6M is less than or equal to 48. Where did they get that one? 48. Okay. Each team has no more than 2 coaches and 14 athletes. Each car can take 4 team members and each minivan can take 6. So what they did is they said each car can take 4. So 4 times the number of cars is the total number of players and coaches. And 6 times each minivan, since each minivan can take 6, is less than or equal to 48. And 48 came from each team has no more than 14 and 2 athletes. And there's 3 teams. Well, 14 plus 2 is 16. 3 teams is going to be 48 players. So that's how she came up with this one. The total number of people is at less than or equal to 48. Okay, because that's the most you could take. Okay, she wrote these linear inequalities to represent the 3 limiting conditions. Here she went to the maximum number of team members is the number of teams multiplied by the maximum numbers of coaches and players. So 3 times 14 plus 3 times 2. She did it that way. Okay? Now she did something called an objective function. And an objective function, oh, I don't know why my screen just did that. Okay. Objective function is an optimization, the equation that represents the relationship between 2 variables in the system of linear inequalities and the quantity to be optimized. So how do C and M, the number of cars and minivans, relate? And she said, let V represent the total number of vehicles. V is equal to C plus M. And that is a quantity to be minimized and maximum. This school wanted to know what's the minimum amount of vehicles and what's the maximum. So minimum makes sense if you're trying to minimize costs. But sometimes in a team, if you do the maximum number, you're going to drive there and you're going to be a lot more comfortable. So maybe they want to know, well, what's the most amount of cars we could take given what we have. So then what she did is she graphed. Okay. She graphed the 3 and then she shaded in. Notice it's orange and it's green dots, and that has to do with the fact that it's discrete. You can't have halves. Okay? I think I could use the objective function to determine each point, but I'm not certain how yet. So this was her feasible region. So any of these points in here, oh, I don't know why my pen's not working. Let's see. There we go. Any of these points in this shaded in area, if she plugged in, it would satisfy all of her inequalities, all of her restraints, and somewhere within that region is her maximum and her minimum. And that's what 6.4 is, just setting up the regions, and then 6.5 is saying where those regions are. And what 6.5 says is, wait a sec, you don't need to check every single point. You only need to draw out the feasible region as if it was a polygon, as if it were a shape, and then only test the vertices of those shapes. That's what 6.5 says. In these spots, in those vertices is where you're going to find the maximum and the minimum, your solution. Okay, let's try another example together. A toy company manufactures two types of vehicles, racing cars and sport utility vehicles. Because of the supply of the materials is limited, no more than 40 racing cars and 60 sport utility vehicles can be made. Okay, let's look at our steps here for a sec. Let's skip ahead. What we always need to do is identify the quantity that must be optimized, look for keywords such as maximize or minimize, and then step 2 is define the variables. So let's just read ahead and then we'll define our variables. Oh, I see it right here. The company wants to know what combinations will result in the minimum and maximum costs and what those costs will be. So cost is really what we're trying to optimize. So step 1 is figuring out what we're optimizing. Step 2 is saying, let's set some variables. Well, let's let R be the number of racing cars, and let's let S be the number of SUVs. Okay? Now we need some restrictions. Well, R is going to have to be a whole number, and so is SUVs, because we can't make half cars, we can't make negative cars. Now some more restraints. Because the supply of material is limited, no more than 40 racing cars. So racing cars is less than or equal to 40. 60, no more than 60 sport utilities. So S is less than or equal to 60. However, the company can make 70 or more vehicles in total each day. So R plus S and 70, there's some relationship. It can make 70 or more vehicles per day. So is greater than or equal to 70. It cost $8 to make a racing car and $12 to make a sports utility vehicle. Okay, so that would be our cost. So this is this is something called, and let's flip ahead to get the right word here. So we define the variables. We have now we need to write a system of linear inequalities. We just did that. We're going to graph it in 1 second. We have to write an objective function to represent the relationship between the variables and the quantity to be optimized. So that's what we're doing right now, is a statement, okay? So C is objective function. The cost is equal to $8 for each race car plus $12 for each sports utility. There's our objective function. So what we're going to do is we're going to graph these here inequalities. We're going to get a feasible region, and then we're going to test out the spots where that makes sense. We're going to test out the spots and plug them back into this spot right here to see which ones give us the max and min. Okay, so I'm going to press pause. I'm going to get my graph ready, and then I'm going to, well, you won't even notice that I pressed pause. Okay? Okay, so I've set up the graph here, and I want to highlight a couple of qualities of this graph that make it really good. It has a title. Each axis is labeled. This is the number of SUVs, and I have a very clear scale. Okay, this is the number of race cars, and again, a very clear scale that shows what that means. So now what we need to do is we need to graph. Remember, these are whole numbers, so we're going to use green dots, and we're going to shade in with orange. So it says each R is less than or equal to 40. So that means that it's all along 40 right here. So that's going to be where the line would be. Now, am I talking about the region over here or the region over there? Well, it says it's less than or equal to. If I chose test points to test, I know that I'm going to talk about the regions over here. So I'm just going to, for now, put some arrows there to remind myself that's where I'm talking about. Okay, each S is less than or equal to 60. So I'm really talking about this line. This is when S is equal to 60, and I'm talking about all the values less than that. So I'm going to put it, so far it looks like I have this square that I would shade in, but I have one more inequality, and that is R plus S is greater than or equal to 70. So I'm going to set this up like a line. So this is like Y, and this is like X. So I'm going to solve for Y. So I'm going to solve for S. So S, and I'm just going to put equals to for now, just so I can draw a line, is equal to 70 minus R, or S is equal to negative R plus 70. And this is like Y equals mx plus b. So my y-intercept is 70. Okay, then my slope is negative 1. So if I go down 1 over 1, down 1 over 1, down 1 over 1. So it looks like I have a line that looks like this. And that's probably about as far as I need to go in order to imagine that line. And now am I talking about the region here or the region there? And if I wasn't sure, I'd choose a test point. And the test point that I'm going to choose is 0, 0. That's always the easiest test point to do. So if I put 0, 0 into my equation, it's right. I'm talking about the region below the line. And if I put 0, 0 in and it's wrong, I'm talking about the region above the line. Okay, so I'm going to go back to my original one, which was R plus S is greater than or equal to 70. Okay, so this is 0 plus 0, because my test point was 0, 0. It's greater than or equal to 7. Is 0 greater than or equal to 70? No, not at all. So I'm really talking about the region above this line. So what I'm talking about right here is this region right in here. So I would shade it in orange, like it says. And because it's discrete, I would have green dots at every point to show. Okay, and there actually should be a whole lot more green dots because each box for me was 5, but it really should be each. There should be a bunch of green dots there. So this is the region that represents this inequality. Okay. Okay. Let's look what it says here. No, actually, this is what I'm going to do. I'm going to go ahead and look at, these are the notes from 6.5. So now what we do is the optimal solution to the objective functions are represented by points at the intersections of the boundaries. If one or more of the intersecting boundaries is not part of the solution, the optimal solution will be nearby. This is what I want to say. You can verify each optimal solution to make sure it satisfies each constraint by substituting into the linear inequality. Okay, so what we're going to do is we're going to test each of these points. So it looks like the intersecting points are going to be this point right here, which is 40 and 30. Another intersecting point happens right here, which is 40 and 60. And the final one happens at, looks like 15 and 60. So what I'm going to do is I'm going to sub this into my my objective function. And remember what my objective function is. Right back up here. My objective function was C equals 8R plus 12S. So I want to know maximum and minimum cost. C equals 8R plus 12S. C equals 8R plus 12S. So what I'm going to do is I'm going to sub each point in and I'm going to see what my cost is. So first I have 15 and 20. And remember, 15 is the value of R. Okay? So here, cost is equal to 8 times 15 plus 12 times 60. Okay? So 8 times 50 is going to be 80 plus 40, which is going to be 120. 12 times 60 is going to be 10 times 60, which is 600, plus another 120 is 720. Okay, so that's going to be 840. So we're going to see, is that going to be a minimum or a maximum? We'll see. The next one is 4060. We're going to sub in. So cost is equal to 8 times 40 plus 12 times 60. So I'm going to go 8 times 40. 8 times 2 is 16. 8 times 4 is 32. With 0 plus 12 times 60 we already saw was 720. So this is going to be 1040. So already this is maximum, but there's still one more point, which is 4030. Okay, so cost is equal to 8 times 40 plus 12 times 30. Okay, 8 times 40 we already saw was 320. 12 times 30 is going to be 360. Okay, adding that together, I get 680. Okay, so it looks like if we wanted to maximize the cost, this would be our solution. And if we wanted to minimize the cost, this would be our solution. Okay? And if we went back 40, 60, 40, 30, we should also double check that those satisfy each of our restrictions. Okay, is it less than or equal to 40? Is it less than or equal to 60? I see that already. If you add those two together, are those greater than or equal to 70? Are each of those greater than or equal to 70 if we add them together? Yeah. So they satisfy all our inequalities, all of our entire system. So that means that they are correct. So I want you to try both the questions from 6.4 and 6.5. These steps in your textbook are really nice. It's good to always have this page open and go through and make sure you do those steps, because these are the steps I'll be looking for on the pretest and the test. And then these are the steps again. This just talks about the optimal solution is going to be found at those vertices of your feasible region, of your shaded in region.